Okay, so for the first week of this chapter, we are going to talk about square roots. Okay. Section 9.1 is going to be stretched over like 4 days, not counting tomorrow. Tomorrow is like such a small day. Where we'll talk about simplifying, adding, subtracting, multiplying, dividing, involving radicals, and then we'll review and take a quiz. Okay? After the quiz, then we'll do 9.2 on. Okay? So it's kind of, it feels a little bit unbalanced, but just trust me. Okay? All right. So when we talk about radicals, okay, this symbol right here, that is what we call a radical. Okay. Now, the number inside, and we're going to even have some variables inside, this is called the radicand. Okay. And then this little number right here is called the index. Now, when we talk about cube roots, we have a little 3 there. When we talk about fourth roots, we have a little 4 there. But when we talk about square roots, do we see a little 2 there? No. When we see a square root, there is not going to be an index. Because, oh my gosh, I shouldn't, n equals 2. If there's not an index, we know that it's a square root, n is 2. Okay? Now, let's list off the first 12 perfect squares. I'll start. 1. 4. Yell out the next one.
9. 16.
16. All right, more than a couple people. 25. Then 36. 49. 64. 81. 100. 121. And 144. We could keep going, but those are at least the first 12 perfect squares. So that means when any of these numbers are under a square root, we can simplify it to an integer. For example, what is the square root of 16?
4.
The square root of 16 is 4. Okay, now, over here we have 2 times the square root of 121. What is the square root of 121? 11. So this becomes 2 times 11, which is 22. Okay. Now, if you're not sure if 289 is a perfect square, you could take the square root and see if you get a nice number. What happens when you take the square root of 289? On the square root, you need to press the second button, and then this guy is second, the square button. Like the x squared button. If you press second and then x squared. Okay. So we have 6 times what? 17. What about the square root of 400? Ah, so this is just 3 times 20, which is 60. Now, it is beautiful if we have a perfect square underneath the radical. But most of our day is going to be spent with non-perfect squares underneath the radical, and we need to reduce them to a simplified irrational number. Okay? So, I am going to show you 2 different ways we can do this, and you can pick which way works best for you. Okay? So, the square root of 32. Okay? In this list of perfect squares, is there a number that can divide into 32?
No. Yes, 4, 84, 62.
Ah, 16, right? So we could say, so here's way number 1. We could say, okay, 32 is the same thing as 16 times 2. Do you agree? Yes, Miss Homie. Okay. What is the square root of 16?
4.
So then we could write this as 4 square root 2. That's way number 1. Okay. Here's way number 2. Way number 2 is we take 32 and we create a factor tree. Okay? So give me 2 numbers that multiply to 32.
1 and 32.
Besides 1 and 32. 4 and 8, right? 4 is 2 times 2. 8 is 2 times 4. And 4 is 2 times 2. So these numbers right here, 2 times 2 times 2 times 2 times 2 is 32. Okay? Perfect squares can come out of the radical. So here I have 2 times 2. Well, that's 2 squared. So 2 comes out of the radical. Here I have 2 times 2. Well, that's 2 squared. So that comes out of the radical. Does this guy have a friend? No. So he has to stay underneath the radical. Hey, we get to the same answer. Okay? Now, this one takes up a little bit more space on our paper, but it's very straightforward. This one, you're going to have to use your brain maybe a little bit more to come up with what's the biggest perfect square that divides into it. Okay? So we're going to do the same thing with 180, and then you're going to kind of think of which way you like better. Okay? So the square root of 180. Can anybody figure out a perfect square that divides into 180? What?
9.
Okay, but it's not the biggest one. Use your calculator. Ah, it's 36 times 5, which means our answer is 6 square root 5. Okay, let's talk about the second way. Okay, 180. My mind goes to 18 times 10, right? 18 is 9 times 2, and 9 is 3 times 3. 10 is 2 times 5. So we're looking at the very ends of our factor tree. Do we have pairs?
3.
We have a pair of 3s, a pair of 2s, and a loner 5. So 3 times 2 is 6. We still get 6 radical 5. Okay? Raise your hand if you really feel like way number 1 is better for you. Raise your hand if way number 2 is better for you. Okay, so how about you try numbers 7 and 8 and see if you can get an answer for me. You pick the way you want. I have no problem with you talking to your neighbor about it. So my suggestion would be to make the factor
What you're supposed to do is, oh wait, you don't have to solve it. I said, no, I
It'd be 7 radicals.
I didn't think.
The pair of 7 times 1.
So, do you know how to do this? You just have to guess which of these feel like I would be. I just had to guess until I made it. Is there an easier way to do that?
Nope, that's why I think sometimes this way would be
11, right?
I love it, yeah.
It's only like 5 by 2.
I'll say if it's 2 times the square root of 21.
These are not.
Hey, you don't have to do both ways. Just get one answer by picking a way. You don't have to do the problem twice. Okay.
There's 2 ways.
What?
You can make a factor tree, and then take all these
Okay.
bottom
Are you sure it's 25
and you can do this.
Okay.
So, you take the perfect square.
Okay. Vivi, did you get an answer for number 7? For this one?
Yeah, I got 7, and then the radical, and then
Okay, Vivi got 7 radical 3. Do you agree? Okay. Now, I had some people asking me, if I do the first way, do I have to start just like guessing and checking to see what divides into the number? Kind of, yeah. Whereas if you use the factor tree, it might be easier. Like if you have an even number, you know that 2 is a factor. And then you can kind of like break it down from there. Okay? Isn't this 49 times 3? So we have 7 times 7 times 3, which is how we get to here. Okay? 175. That one's maybe a little bit easier to see which perfect square divides into it. Because what is it? It's 25 times 7, right?
Yeah.
So we have 5 radical 7. Okay. Now, here's the trouble that I'm worried about us getting into if we use way number 1. What's a perfect square that divides into 48?
12 and 4.
Oh, okay. I know 4 times 12 is 48. So this becomes 2 radical 12. Is that simplified?
No.
It's not, because 12 still has a perfect square. Okay? So we have to be careful and make sure we're pulling out the biggest perfect square. Okay? Now, we know that this is 4 times 12, right? And 12 is 4 times 3. I can keep going with my 2's, but I also see that I have a pair of 4's. This is going to be 4 radical 3. Okay? Or we say that the square root of 48 is 16 times 3, so we get 4 radical 3. Theo, did you have a question?
No.
Sorry, I thought your hand was up. Okay? Yeah.
Does 16 not go into 3? It does.
Yeah. It's 16 times 3.
Oh.
Yeah. On my factor tree? Okay, so what I did, I know that 4 is 2 times 2. But since I had a pair of 4's, I decided to stop just to save myself some time. Is that okay? Yeah. All right, now what happens if there's a number out front?
You would just sit, I'm guessing it's just you need to simplify. And mine is that first you need to find the square. You need to find two numbers that go into there that have perfect square. Then you probably need to get the thing out. And then my guess is that then you solve like a normal problem, but you multiply with the 2.
Okay, so that 2 is being multiplied to our radical. So let's simplify the square root of 54. Thoughts? We know that this is 9 times 6. Is that my factor tree?
No.
No? You don't agree?
Didn't you multiply 2 and 54?
Not yet.
Okay.
Okay? So, what's going to happen is this 2 is still there. And we're multiplying it to 3 comes out of our radical. And left over are my 2 loners, 3 times 2. We're not done yet, okay? So then, whatever is outside of our radical can get multiplied together. Okay, that radical is a wall, and the only way to get out of it if you're a perfect square. So I got to take 3 out of it because I had 3 squared. But otherwise, these two numbers don't mix. Okay? All right, turn to the top of page 2. And I am going to have you try... number 11. You try number 11. You're just having a rough week.
I know. Like everyone's just
Okay. Would you raise your hand if you made a factor tree? Some of you have changed your tune since 5 minutes ago, huh? Okay. Did you start out with 15 and 10?
No.
Really?
No.
Interesting. Okay. So some of you started out with 25 and 6 and bam, you were ready to go, right? But maybe you started out with 15 and 10, 3 times 5 and 5 times 2, right? Okay. Make sure that that -5 stays out. Who gets to come out of the radical?
5.
The pair of 5s come out as a 5 and under the radical?
2 and 3.
So we have -25 radical 6. Is that what you got?
Yes.
Okay. What I want you to do, we still have a few more notes to go. It's kind of broken up into 2 sections. Will you just turn to page 3 and circle the problems 1 through 12? Just circle the problems 1 through 12. And then go to page 4 and wait for me. What? Let's look at that at the end, okay? Okay. So now on page 4, we're going to talk about what happens if we have a variable underneath the radical. So we've talked about if we have numbers underneath the radical. What if we have a variable underneath the radical? Okay. So, basically, anytime we have a pair of 2's, it comes out of the radical as a 2. If we have a pair of 3's, it comes out of the radical as a 3. Do you see what I'm saying? Yeah. So if we have a pair of A's, it would come out as an A. Okay? So whatever happens, like if we have an even exponent on our variable, it's going to come out of the radical cut in half for the exponent. Like the square root of a squared is a to the first. The square root of a to the fourth would be a squared. Do you get what I'm saying there? The square root of a to the 10th would be a to the 5th. Okay? If it's not a multiple, if it's not an even exponent, then we're going to have a leftover guy. Okay? So, number 1, the square root of x squared is just x. Okay. All right, so now let's throw some numbers under there too. The square root of 9k to the 10th. Well, what's the square root of 9?
3.
Okay. What's the square root of k to the 10th? K to the 5th. Duh. Okay. Now, not all the time are we going to have perfect squares. Okay. So let's talk about this square root of n to the 5th. That's an odd number, correct? So what I'm going to do is I'm just going to rewrite it as n to the 4th times n to the 1st. Is that still n to the 5th?
Yes.
Okay. What's going to happen, bless you, n to the 4th under the square root, we can simplify that to n squared. But then I have a loner n who has to stay underneath the radical. So sad. Okay. let's talk about number 4. We got a lot going on in number 4. We have 40 a to the 19th underneath our radical. Okay. So let's focus on our numbers first. Okay. 40, I'm going to make a factor tree. First thing that comes to my mind is 4 times 10, right? Okay. What comes out of the radical? 2 times 2 comes out of the radical as 2. What stays underneath the radical?
10.
Okay, 2 and 5, which is 10. Okay. Now we got to focus on our a to the 19th. Since 19 is an odd exponent, I'm going to break it up to be a to the 18th times a to the 1st. So if I have the square root of a to the 18th, we get to pull it out as a to the 9th. And then our loner a gets to stay with the 10. What's your question, Joey?
Where did you get the 9 exponent from?
Okay, so if I have the square root of a to a power, we can take out pairs, right? So I basically have 9 groups of a squared. So a to the 9th comes out. Does that answer your question?
Or
Okay.
Or maybe could like another strategy just basically be like multiply the one that has an exponent above 1 by 2.
Well, divide it by 2.
Yeah.
Yeah. Yep. Yep. Okay, I want you to try numbers 7 and 8. I want you to try number 7 and 8.
Or would it just be? No, it could just be b to the first. Because if you have the two numbers that have an exponent of 1, it will become 2 squared. Okay, for these two, we have 9, 7. No. I was like, what? I was like, when you were asking for
Well, you leave at 2:30, right?
That's the person that got 3 b because that's 7.
Is that a 7 or a 9? 7?
Another one was 9.
All right, Rachel, what'd you get for your answer in number 7?
I got 3b and
3b radical 7. We know that 63 is 9 times 7. So 3 squared is underneath, so 3 comes out. B squared is underneath, B comes out. There's our answer. Excellent.
what happened to the other b?
Well, the square root of B squared becomes B. Yep. Tinley, what do you think about number 8?
3n squared, and then the thingy, and 3n. 3n squared.
Okay, Tinley's not sure. Is there a square here or no square?
Square.
Okay, so 27 is 9 times 3. So I think we're all okay with your 3 coming out here. But then we have n squared times n. Well, if n squared is under a square root, it comes out as n to the first. Okay. Thank you, Jill. All right, let's come down here to number 11. 11's got a lot going on, but it's okay. We're just breaking it apart, okay? So this is what I'm going to do first. I'm going to make a square root. I'm going to write 128. I'm going to write p to the 4th times p, q squared, and r to the 18th. Why do you suppose I did that? Okay. Now, this is going to help me stay organized. 128. Anybody want to tell me 2 numbers that aren't 128 and 1 that multiply to 128? What do you think, Theo? 2 times 64? And 64 we know is 8 times 8. Are you cool if I just stop there?
Yes.
Because I know, hey, 8 can come out, but the loner 2 has to stay behind. Okay, let's talk about our p's. What comes out of the radical for the p?
P to the second square.
P squared, but then we have a loner p left behind.
So it goes.
Yep. Okay, what about the q's? What comes out?
Q.
Just a q? Uh-oh, I ran out of room. And then, nope, there's no loner q.
R to the 9th.
And then r to the 9th. Since q and r have even exponents, we will not have anything under the radical for those variables. Okay? Okay, so make a note to yourself that on page 6, you're going to do numbers 1 through 8.
Why did we circle 1 through 12?
But that was on page 3.
Is that homework?
Okay, so your homework is coming from